Hello everyone, welcome back to the Aerosouls training program. Today we are starting with the module 2 of the program. Before we start with, I would like to inform you all what all things we covered in the first module, that is Introduction to UAV, which was divided into 4 units. Unit 1 was History of UAV, which covered how did drone evolved to the drone we see today. Unit 2 was about all the stakeholders, in which we understood that who are all the people involved in the drone industry, and we also understood the minute roles and responsibilities of each stakeholders. Unit 3 was all about the drone laws and regulations, specifically Drone Rules 2021 and their amendments. Unit 4 was all about the mandatory third party test, in which we understood that what are all the exact tests that a manufacturer had to conduct in NABL accredited lab before even filing for the type certification, that is D1 application. In short, module 1 was the full picture of a drone from outside. Today we are starting with the new module which will be all about the anatomy, manufacturing or assembly of a drone. In short, we are going inside the drone. Now, everyone among you might have questioned, if you want to learn a drone, why are we talking about the principles? Here's the answer to your question. A drone is an aircraft, whether it has wings or propellers, it still have to fight with the same forces that every aircraft fights with. Gravity wants to pull it down and air wants to slow it down. So understanding how every flights work is the foundation of everything. Once you understand this, everything else, the motors, the propellers, the design will make a perfect sense. So let's begin. The topic of the today's video is Introduction to Principles of Flight, in which we will cover the aerodynamics, forces, control surfaces and flight mechanics. And one thing I want to be very clear with, we are going to keep this very simple. No complicated math, no confusing jargon. Each and everything would be explained with a simple example. Before we start with how the flights work, let's first understand some important keywords. And don't worry, I will explain each of this in detail in the upcoming slides. So let's first understand what is airfoil. First one, the airfoil. Let's understand the airfoil with the help of the 3D model. You can see the 3D model of the aircraft. There is a complete model. First one, as I said, the airfoil is the cross-sectional shape of the wing. Let's explode the same aircraft and find all the airfoil. As you can see, there are multiple airfoil across the wing. Okay, so all this minute part across the wing are called airfoil. This is the complete airfoil of the wing. And this special shape is what that create lift. Next, the chord line. Let us understand what is the chord line in the 3D model. So, in this airfoil, the front of the airfoil is called as leading edge and the end of this airfoil is called as trailing edge. So, when I join these 2 points with an imaginary line, then this particular line is called as chord line. This particular line is called as chord line. I hope it is very clear. Next, the relative wind. Relative wind refers to the direction of the airflow relative to an aircraft's flight path or aircraft's motion. Suppose when you drive fast on a bike, you feel air hitting on your face. So that feeling from aircraft perspective is relative wind. Let us understand in short what is relative wind in the 3D model. The nose is heading towards the east, so the airflow towards the west is the relative wind. Next, angle of attack, which is the angle between the chord line and relative wind. Angle of incidence, which is the angle between the chord line and the aircraft's longitudinal axis. We'll see both of them in detail in the upcoming slide. Next, the Bernoulli's principle. This is a scientific rule that says faster moving air creates lower air pressure, and this is one of the reasons why wings create lift. Next, the center of gravity. This is a point where the entire weight of the aircraft acts just like a balancing point of a seesaw. Next, the center of lift and the center of pressure. These are the points where lifting and aerodynamic forces acts on the aircraft. So, all of these are core important words in the aircraft that you must remember, and you can consider all of this as a building block for an aircraft. Now let us understand what's the airfoil and how the airfoil creates a lift for the aircraft. The top of the airfoil is curved like a straight hill and the bottom of the airfoil is flatter. Now let us understand why this shape is important. So let me explain this with a simple example. Imagine the two cars racing on a road. Car A takes the straight road and car B takes the longer curved road. And if both the cars have to reach the finish point at the same time, the car B has to keep up with the top speed. The same thing happens with the air hitting the wing. When the air reaches the wing, gets splits. Some air goes over the top of the wing and some air goes under the bottom. As the top surface of the airfoil is longer and curved, the airflow going over the top, so it has to move faster to keep up. And here's the thing, faster air creates lower pressure. The pressure above the wing is getting lowered and the pressure creating under the bottom of the wing is higher, due to which wings get pushed upward with this pressure difference. And this is the fundamental secret how every fixed wing aircraft or even the drones generate lift. So first, let's understand what's chord line. This is the 3D model of the aircraft which I have already seen while understanding the words. Let me walk you through again what is the chord line. So this is the front of the airfoil which is called as the leading edge, and this is the end of the airfoil that is called as trailing edge. And when we join the imaginary line between these 2 points, thus this line is called as chord line. It is just like the spine of the wing. It never changes whether the aircraft is climbing, diving or turning. It remains always fixed. It is a reference ruler in the sky. So keep all this thing in mind. Now let's understand what's relative wind. When the aircraft moves forward, air flow towards it from the front, and it is always opposite to the direction of the aircraft is moving. In short, relative wind is the direction of the airflow relative to the aircraft's flight path. So you have to keep all this thing in mind. And an important point, chord line and relative wind together make an most important definition in the field of aviation, that is angle of attack. In every airfoil, there is an imaginary line running from front and back exactly between the middle of top and bottom surfaces, which is refers to as mean camber line. If the top and bottom surfaces of the wing are equal, just like a flat board, then the chord line and the camber line are same, which is also called as symmetrical airfoil, used in aerobatic aircraft. But most of the aircraft wing have more curve on the top, so the camber line curves over the chord line and the amount of curvature is refers to as camber. More camber refers to more lift at low speed. Less camber refers to less drag at high speed. And the aircraft designer choose the right camber for the right job. For drones and fixed wing UAV, understanding camber help us choose right wing profile for the efficient flight. Now, this is the most important definition in aviation, so please pay close attention. So what is angle of attack? Angle of attack is an angle between the relative wind and the chord line. So when I just simulate this straight line, this angle that is being created, that is the angle of attack. Let me explain the same thing with our 3D model. When I tilt the nose of the aircraft little bit up, you can see the changing angle between the relative wind and the chord line, and that changing angle is called as angle of attack. But when the same angle has been increased like this much, this particular situation is called as stall. So what's stall now? When an angle of attack increases the critical angle of attack, which is roughly 15 to 18 degrees, the smooth airflow over the wings breaks apart and it becomes chaotic and turbulent. And finally, the wing stops generating lift. So, at this scenario, very terrible things can happen. And here's the important thing I want you to remember: the stall is not going to too slow, but a stall is not going to too high an angle of attack. You can stall a wing at any speed if you pull up too sharply. This is why pilot and drone operators always monitor the angle of attack. Here is a quick but important distinction. Just look at the 3D aircraft. Where are the wings connects the body of the aircraft? This is called the fuselage. Here you can see the angle. The angle at which wing is permanently fixed to the fuselage at the time of manufacturing is called angle of incidence. And importantly, on most of the commercial aircraft, this angle of incidence is about 2 to 4 degrees, which means you cannot change the angle of incidence during the flight. It is set at the factory. But the angle of attack always changes whenever the aircraft climbs or dives, or even cruise. Simple way to remember: angle of attack is fixed and set during the manufacturing, it never changes, and angle of attack is variable, which changes every moment in flight. This is the heart of all flight physics. Every aircraft, whether it is a fighter jet or DJI drone, is constantly fighting and balancing the four forces. Let me explain this with a simple picture. Lift is the aerodynamic force that always acts upward and generated by the wings and always fights with gravity. Weight is the aerodynamic force that acts downward, and it is by pull of gravity on the aircraft. It always tries to bring it down. Thrust is the aerodynamic force that acts forward, generated by the engines or propellers, which pushes the aircraft. And fourth aerodynamic force, which is drag, that acts backward, created by the resistance of air on the aircraft, which always tries to slow it down. For level and straight flight, these four forces must be balanced. Lift and weight must be equal to attain same altitude, and thrust and drag should be always same to have same speed. If the thrust is more than drag, the aircraft accelerates, and if the lift is greater than the weight, the aircraft climbs. Simple as that, everything in flight is managing these forces. Let's look at the first aerodynamic force, that is thrust. Thrust is the force that pushes the aircraft forward. Without thrust, there is no forward movement. Without forward movement, the wings don't generate lift. And without lift, the aircraft falls. The physics behind the thrust is the Newton's third law. Every action has equal and opposite reaction. Let's understand this with simple examples. In a propeller aircraft, the propeller spins and pushes the air backward, and in reaction, the aircraft is pushed forward. In a jet engine, the engine burns fuel and blasts exhaust gases backward, and in reaction, it shoots forward. In a jet engine, the engine burns fuel and blasts exhaust gases at high speed, and in reaction, the aircraft pushes forward. In our drones, the spinning propellers pushes the air downward, and in reaction, the drones gets pushed upward. In all these three examples, same principle have been applied. Sources of thrust include piston engine with propellers, like in small aircraft, turbogen jet engines in commercial aircraft, turboprop engines in regional aircraft, and rocket engine for extreme performance. Each of them has same job: overcome drag and create forward or upward motion. Now second aerodynamic force, the lift. This is a force that keeps the aircraft in the air. Now on the screen here is the equation of lift. Let me break down in short. Here L means lift, which refers to the force that we want to generate. Rho means the air density. Rho refers to the air density, which means how thick the air is. Important note, at higher altitude, the air is thinner, which creates less lift, and therefore most of the aircraft struggle at higher altitudes. V square refers to the velocity square, which means the speed of the aircraft. And here important note, if the speed of the aircraft is doubled, the lift generated by the aircraft would become 4 times stronger. So the speed is very critical for the lift. S refers to the area of the wing. The bigger the lift, the more lift it can generate. Therefore, the cargo aircraft has huge wings. CL refers to the coefficient of lift, and this depends on the shape of the wing and the angle of attack. So to summarize in short, you get more lift by going faster, flying in denser air, or increasing the angle of attack. This is why fixed wing UAVs needs to build up speed before it can take off. It needs enough velocity to generate sufficient lift. The third aerodynamic force, that is the weight. It is the gravity pulling the aircraft downward. Weight includes everything on the aircraft: the empty aircraft structure, passenger, cargo, payload, sensor installed on it, that is everything. In fact, also the fuel into it. An important note you need to remember, weight changes during flight. As fuel burns, the aircraft becomes lighter. That is why long flight becomes more fuel efficient towards the end. Lighter aircraft needs less lift. For stable flight, the lift must equal with weight at all time. For UAV operator, maximum takeoff weight is a critical number, and it should be kept in mind. If your drone is too heavy, it cannot generate enough lift, and that is why every drone have a weight limit. That is why we carefully calculate the weight of every payload, sensor or camera that is mounted on it. The fourth aerodynamic force, that is the drag. It is the air resistance that opposes the aircraft's forward motion. Drag always acts backward and opposite to the direction of the aircraft's movement. The equation of drag is similar to the equation of lift, and it depends on the density of air, the velocity squared, the shape of the wing, and the coefficient of drag, which specifically depends on the shape of the aircraft. Very important observation. Drag increases with square of the velocity. So, if you double the speed of your aircraft, the drag increases 4 times. That is why supersonic aircraft needs enormously powerful engines. There are two types of drag: parasitic drag and induced drag. Parasitic drag increases as you go faster. It is the drag created by the body of the aircraft regardless of lift. And induced drag decreases as you go faster. This drag is created as a side effect of generating lift. Together they form U-shaped curve where the total drag is minimum. Aircrafts cruise at this speed to get best fuel efficiency. We call this maximum aerodynamic efficiency point. Let's get deeper into the types of drag because it is very useful for the drone engineers. Parasitic drag is a drag which exists even when the aircraft is not generating lift, which has 3 different types. First, skin friction drag. It is created due to the friction between moving air and the aircraft surface. Smoother surfaces reduce this drag by maintaining the cleaner airflow. Since the skin friction drag contributes significantly to the total parasitic drag, surface maintenance and aerodynamic finishing are important for efficiency. Second, the form drag, which is also called as pressure drag, and it is created by the shape of the aircraft. Blunt or poorly streamlined structures create larger wake regions behind them, increasing the pressure difference and drag. Streamlined design allow the air to flow more smoothly around the body, reducing the turbulence and improving aerodynamic performance and fuel efficiency. Third, interference drag. Interference drag is created where two or more aircraft surfaces meet, such as at wing fuselage or landing gear junction. Airflows from different directions interact, creating turbulence and additional drag. To reduce this type of drag, engineers use fairings and fillets that smooth airflow transition, improving aerodynamic efficiency and improving overall aircraft performance. The next type of drag is induced drag, and it is a drag that is generated as a byproduct of lift generation. It occurs because high pressure air beneath the wing flow towards the low pressure region over the wing, creating wingtip vortices. And these vortices generate a rearward force that opposes the forward motion. Induced drag is highest during the low speed flight, such as takeoff, landing, or climbing, when higher angle of attack is required to generate lift. As the speed of the aircraft increases, the drag decreases significantly, following an inverse relationship with the velocity squared. Winglets and optimized design wings helps reduce induced drag and improve the aerodynamic efficiency. The next is wave drag. It is a compressibility related drag and it occurs when the aircraft approaches the transonic speed, typically around Mach 0.8 and above. At this speed, airflow over the parts of the aircraft becomes locally supersonic, leading to formation of shock waves. And these shock waves cause energy losses and sharp increase in drag. Aircraft designers reduce the wave drag by using swept wings or area rule fuselage design. Wave drag is important for high speed aircraft and it is completely irrelevant for the commercial aircraft and even drones. Here is something really fascinating, the Coanda effect. Let me explain this with a simple experiment that you can do at home. Take a spoon and hold it near a running tap of water, but don't put it in the water. Just bring the curved back of the spoon close to the stream. You will notice that the water curves and follows the shape of the spoon. It sticks to the curved surface instead of flowing straight. That's the Coanda effect. The same thing happens with the air over the wing. When the air flows over the top curved surface of the wing, the air does not fly off in a straight line, it follows the curve of the wing. And this creates a low pressure zone over the wing. And that's the contribution to lift. This was discovered by the Romanian engineer Henry Coanda. In UAV and drone design, the Coanda effect is used in advanced wing design to keep the airflow attached to the wing even at higher angle of attack, improving efficiency and stall resistance. You have probably heard the name Bernoulli, the Swiss physicist who have given the most important principle in flight. Bernoulli's principle state that in a flowing fluid, including air, when the speed increases, the pressure decreases. Let me make this very simple. Think of a river where the river is wide, the water flows slowly and calmly. But where the river becomes narrow between the rocks, the same water has to squeeze through smaller space, so it flows faster. You can observe this at any river. Pinch the end and the water shoots out faster. Now apply this to a wing. The curved upper surface forces air to accelerate to go faster, and faster air creates lower pressure above the wing. The air below the wing moves more slowly, which creates higher pressure below and lower pressure above creates net upward force which leads to generation of lift. This is the fundamental physics of how wings work and it's beautiful in its simplicity. This is why the shape of the wing matters so much. The job of the airfoil is to create exactly correct pressure difference to generate lift needed for the flight. You have learned the Newton's law of motion in class 9 or 10, but this time we are understanding in the context of flight. The Newton's first law of motion states that an object at rest stays at rest, an object in motion stays in motion unless an external force is applied. In aviation, once the aircraft is cruising, it wants to keep going at the same speed. It will only slow down once the drag acts on it. This is why when an engine fails in an aircraft, the aircraft doesn't immediately falls down, it starts gliding forward because of inertia. Newton's second law of motion states that force equal mass times acceleration. This explains everything. The heavier aircraft needs more thrust to accelerate. Lift equation, drag equation, everything is derived from this law. So, if you want your drone to climb faster, you need more thrust force. Newton's third law of motion states that every action has equal and opposite reaction. This is most exciting one for drone. The spinning propeller pushes the air downward and in reaction, the drone is pushed upward. Absolutely everything in propulsion comes from this third law. Three critical balance points of an aircraft. Think of it like balancing a seesaw. First point is center of gravity. This is a single point where complete weight of the aircraft acts downward. It includes everything: structure, fuel, payload. If you could balance the entire weight of the aircraft on your single fingertip, the CG is exactly where your finger would be. The CG point is the most important design parameter. If the CG is too far forward, you can conclude that the nose is too heavy. If the CG is too far back, you can conclude that tail is too heavy and the aircraft becomes unstable and may flip. Every aircraft has a CG envelope, which is a safe range within which CG must stay. Next point is the center of lift. This is where the total upward lift acts on the wing and it is distributed across the wingspan. Next point is center of lift. This is where the total upward lift force acts on the wing. It is distributed along the span of the wing. The third point is center of pressure, and this is where the total aerodynamic force on the aircraft acts and it moves forward as the angle of attack increases. The rule for stable flight is simple. The center of gravity must be slightly forward of the center of pressure. You can note it simply that if the CG is too far back, the aircraft would be unstable, and if the CG is too far forward, the aircraft would be overstable and cannot maneuver easily. When you design or assemble a drone, CG placement is one of the first and most important calculations you make. Aerodynamics is simply a study of how air behaves when it flows around an object. It is a branch of fluid dynamics and we consider air as fluid because it flows. Aircrafts fly in different speed regimes and aerodynamics change significantly at different speeds. Here is how we categorize them using Mach number, which is the ratio of object speed to the speed of sound. For all our drones, we operate firmly in subsonic regime. No shock waves, no transonic effect. We focus purely on low speed aerodynamics. Modern aerodynamicists use computational fluid dynamics, which is a powerful computer software that simulates airflow around a 3D model. This is how drone wings and aircraft bodies are designed and optimized today. Now we get into the exciting part. How do we actually control the aircraft's direction? Let's understand the same thing with the 3D model. On the horizontal tail, you can see the elevator, and then on the tail fin, you can see the rudder. And these are the steering wheel, accelerator, brakes of the aircraft working together seamlessly. Now let's understand each and every control surfaces one by one. First, we'll explore about elevator. Elevator is located on the horizontal tail, you can see, which controls the pitch of the aircraft. It moves up and down. So, when the pilot pulls the stick back, the elevator deflects upward and which pushes the nose of the aircraft upward and due to which the aircraft climbs. And when the stick is pushed forward, the elevator deflects downward due to which the nose of the aircraft goes downward and the aircraft descends. Next control surfaces is ailerons. Ailerons are located on the trailing edge of each wing. You can see over here, these are the ailerons. And most important thing you need to remember, they always work in opposite direction. That means when the right aileron goes up, the left aileron goes down. Let's understand how ailerons work. When the right aileron goes up, the lift on the right aileron reduces, and on the other side, the left aileron goes upward and the lift on the left aileron increases, due to which the aircraft rolls right. And this is how turns are initiated in a fixed wing aircraft. Next control surface is rudder, and rudder is located on the vertical tail fin. When the rudder deflects left, the aircraft yaws left, and when the rudder deflects right, the aircraft yaws right. The rudder is also critical for crosswind landing. When the wind is blowing from the side, it helps align the aircraft with the runway. So in short, you need to understand elevator controls pitch, rudder controls yaw, and the ailerons control rolls. Now let's put everything together and understand how complete flight happens from engine start to touchdown. First phase is takeoff. The engine powers up with full throttle, maximum thrust is applied, and the aircraft begins accelerating down the runway. At a certain speed, which is called as rotation speed, the pilot pulls back on the stick and the angle of attack increases, lift exceeds weight, and the aircraft lifts off the ground. The landing gear retracts. The flaps, which are extra surfaces on the wings that increase lift at slow speeds, gradually retracts as the aircraft gains speed and altitude. Phase 2 is cruise flight. At cruise flight, the pilot sets the aircraft at a constant speed, lift equal weight, thrust equal drag, and the aircraft is in perfect balance. As the fuel is burned, the aircraft gradually becomes lighter and the pilot makes small pitch adjustment, that is slightly reduce angle of attack to maintain stable flight as the weight decreases. The autopilot in advanced aircraft and drones manages heading, speed and altitude automatically. Phase 3 is landing. Thrust is reduced and aircraft begins a gentle descent. The flaps are extended, that increases the wing area and lift, allowing the aircraft to fly safely at much slower speed for landing. The approach is typically 1.3 times the stall speed, giving a safe margin above stall. Just before the touchdown, the pilot gently pulls up the flare maneuver, reducing the descent rate. The main wheels touch down smoothly and the nose is lowered gently. Reverse thrust and brakes brings the aircraft to taxi speed. The aircraft has completed the flight using every single principle we have learned today. Lift, thrust, weight, drag, control surfaces, all working together seamlessly. As we conclude the session, let's quickly review the key concepts that form the foundation for flight mechanics and aerodynamics. We began by understanding terminologies, which includes airfoil, chord line, relative wind, and angle of attack. Each of them are essential for understanding lift generation. Next, we explored four forces of flight: lift, weight, thrust, drag. In steady and level flight, all of these forces must be balanced, allowing the aircraft to maintain constant altitude and speed. We then examine lift, learning that it is created by pressure difference around wing and it is influenced by air speed, air density, angle of attack, and area of the wing. Then we moved on to drag, understood types of drag along with their causes and method of reduction. We also covered the contribution of Bernoulli's principle and Coanda effect that explains the airflow behavior around the wings, as well as Newton's law of motion, which governs the aircraft movement and propulsion. Finally, we studied about the control surfaces and the three phases of flight. Together, these concepts form the core knowledge for understanding how drones and aircraft fly safely, efficiently, and predictably. This foundation will support all advanced topics you study in aviation and drone operation. I hope this video has made principles of flight very clear to you. And I want you to remember one thing. Every drone you fly, every flight you plan, every UAV you design, all of them are governed with same exact principle that we have discussed today. There is no magic, it is all beautiful science. So, if you enjoyed this video and learned something new today, give it a thumbs up. It really motivates us to keep making a great content. Subscribe to our channel so you don't miss the next video, Propulsion and Vertical Motion, where we will explore how ESC, motors and propellers actually work together to make a drone fly. If you have any question, drop them in comment section and I read every single comment and I'll do my best to answer your doubts. On behalf of entire Aerosols team, thank you for your time, your energy and your passion for learning. Sky's not the limit, it's just the beginning. I'll see you in the next video.